Okay, so in the previous video, we had discussed minimizing cost. Hopefully, we can do the whole thing in one video. We're going to briefly discuss and we'll go over the three different cases. Okay, so we are now ready to tackle the firm's cost minimization problem. The firm has a production function, we know that, and can use labor and capital at the given prices W and R. We ask if the firm wants to produce a certain quantity of output Q target at the lowest cost possible. How much of inputs L and K should the firm use? We will call the optimal choices of inputs L star and K star. So those are just the values such that we reach the Q target and at the minimal cost. So the first condition, as I think I said previously, we can kind of read through this, but this is condition one. It's not really a condition. It's just a statement that says we have a Q target, whatever it may be, and we want to find labor and capital, those two values that fit our Q target, our quantity target. Okay, so that one's just kind of obvious there. So DMRS is exactly the same as saying a Cobb Douglas function. Cobb Douglas function is DMRS. DMRS is Cobb Douglas function. And we don't have to understand the great interpretation of that. Diminishing marginal rate of substitution is what DMRS means. It means, trading some labor for capital, trading some capital for labor. The interpretation is difficult and meaningless, but it just basically is a fancy word for the slope. Yeah. So we know what that is there. I can draw it, but we get to that in a minute. Okay, so we derive condition two for all of them, for the Cobb Douglas, for the linear, and then for the complements. So we kind of go through this here. Strictly convex isoquants, DMRS. This is the same as Cobb Douglas. So there's, we talk about, we don't care about 2.8. We care about 3.9, which is right here. Yeah. 2.8 is from before, and we reiterate it in 3.9, which should be right here on this page. Do we have a 3.9? Yes. So I did do this in a previous video, the last couple. We're kind of reviewing before we move forward, yeah. But basically, isocost and isoquant, that point A, where the isocost and the isoquant, where they intersect, they of course have the same slope there. So we care about the slope at that point A. It will always be that. So that graph there is going to show the condition two for cost minimization. Yeah. So we're going to do an example problem here in a minute. Probably not in this video, another video. But pretty quick, we're going to do an example problem that this is the theory. So defining it that well as condition one and condition two is not that important. But we're supposed to know what's going on in the graph, but the outcome is just that one thing that if you divide the derivatives of what are the derivatives? The derivatives are isoquant. Yeah. And what is this W over R? That's the slope. Yeah, that's the slope of the isocost. Yeah, I'm not writing this in any kind of technical terms. So basically, you have your isoquant, the isocost, and they intersect, and we're only going to use that one point ever. And where they intersect, the slope's obviously equal. It should be obvious if we have kind of a strong math background. Yeah. Okay, so the linear isoquants, yeah, we're going to kind of derive a few basic equations. Like we see in red, the 3.10. If they say 2.9, they do it a lot better than 3.10, which is just right here in front of us. So it kind of goes on there. Yeah. So I think it's just kind of a little bit better. What they're going to do through this paragraph is they're going to derive these, basically the three possible situations. All of them are condition two for the linear. Yeah, the three possible situations that we have for the linear when you compare the isocost and the isoquant. So let's just kind of take a look. What the heck? Okay, so I don't think it's too important to kind of read this paragraph. We can't really describe it too well without reading this. So we kind of read through that explanation and it describes these. Yeah, but we have the kind of the three explanations right in front of us. Yeah, so we have this point here, we have that point, and then we have the third case to the right. But just remember the W over R is the ISO cost. It's just we kind of struggle to say them. Um, okay, so the repetitive one. Yeah, the repetitive one, that is the ISO cost. We just want to, for all graphs, of course, yeah. And then the one blue line, yeah, the one blue line is the ISO cost. I'm sorry, ISO quant. This is not the Cobb Douglas. Remember, this is case 2 of the 3 cases. This is the linear graph. Yeah, it's still, the blue line is still a contour line. It's still an ISO quant. Okay, so it's kind of hard to interpret all the math that they do, but they're just saying that the slope of the isoquant is greater than the slope of the isocost. The slope of the isoquant is less than the slope of the isocost. The slope of the isoquant is equal to the slope of the isocost, isoquant. It doesn't matter what we say there, yeah. Okay, but they just want us to kind of understand that always 100% of the time, when the isoquant slope is greater, right there, technically k equals 0. Yeah. When the isoquant slope is less than, it's always going to be right here. Yeah. The L equals 0. Yeah. What point do we have to be on here? It doesn't matter what point. There's infinitely many points, right? A is going to be infinitely many points. So if the isocost and isoquant are obviously the exact same line, we're trying to minimize cost. Cost is minimized anywhere we are at that. So there are going to be infinitely many values of L and K such that that work. Yeah. So they sum this up. This is condition 2 for the linear. It just shows the 3 cases where the one slope is greater than the other. Remember, so we just understand the very basic thing that this right here always comes from the isoquant, and the other side W over here always comes from the isocost. So I'm trying to kind of do all of it in one video. Cobb Douglas is by far the most important. And then in a kind of distant second is the linear, which we're doing now. And then the one that doesn't really matter at all for the whole book, but we still define it, of the 3 cases, this is the distant third, is of course going to be L-shaped, where we're mixing 2 chemicals or 2 metals or something to make an alloy. Yeah. But just whatever the slope is, I do understand how it could be confusing, because for those isocosts, the black lines, the isocost, the slope is the same for all of them. But we would want to, even though it's not quite in the theory, you know, we have to do an example problem. I'm not going to pretend like it works the way that I explain it. There's a value k right there. That's the k star. There's a value L right here. That's the L star. Yeah. So it's supposed to be the slope of one equals the slope of the other. In real life, an L-shaped graph doesn't exist. We have to make, I don't know, it's not a step function, but we have to make that exist. There's no slope at the corner. We only care about the slope. We only care about the slope of the isocost, and we care about the value of K and L that work there. Yeah. So maybe they tell us just a little bit. For time's sake, we're going to fly through. Okay, so finally, they also agree that who cares. In the next video, we're going to construct the cost function. Yeah. So this is the condition 2 for the third, and we'll move on into the next video here.